This is the recursive algorithm for binary search tree search. We want to search out a node in binary search tree. Now, binary search tree we have already covered, and we know that binary search tree has the property that all the nodes on the left hand side of a root have values lesser than the root, and all the nodes on the right hand side of the root have values greater than the root. So this is a recursive algorithm for searching out a node in a binary search tree. Now let me explain to you the algorithm, and with an example I will explain how it is working. Now let's take this binary search tree and let us search out the node 13 from the tree. So this is the binary tree, this binary search tree, this is the root, and we want to search out the number 13. So therefore when you are calling the search algorithm, you would be calling search with node 4, that is the root of the tree, and the number 13. Correct? Now we will enter the recursive algorithm or function. Now as we have discussed that any recursive function has a base condition. Our base condition would be when our root becomes null. Either we will get the node in the tree, and if we don't get the node in the tree, we will reach a point where our root value will become null. So there we will end the search and we will return a value 0 showing that the node has not been found. And if the node is found, then we would be returning a 1. That is why the return type is given as int. So root not being null is the base condition of the recursive call. So over here our root value is 4. So root value is not null. So you will enter the condition. Now if root data is less than num. Now when we are searching out a node in this binary search tree, how will you do that? You will come, suppose as we know that we want to search out the number 13. Now when you are searching out this number 13, you will come to this node. This is 4, correct? So 4 is lesser than 13, so obviously 13 will lie on the right hand side of 4. So you will go to the right hand side, that is right subtree of 4. Now when you come to 10, you know 13 is greater than 10 as well. So you will ignore the left hand side and you will come to the right subtree of 10. Now when you come to 15, you know 13 is lesser than the 15. So you will ignore the right hand side of 15 and you will come to the left hand side of 15 where you will get 13. Correct? So that is a simple procedure. So that is the same procedure we are doing over here. Root is not null, so we are checking what is the value of the root data and whether the root data is lesser than the number. So over here 4 is lesser than the number, 4 is lesser than 13. So since 4 is lesser than 13, we have to come to the right hand side. We will ignore the left hand side of 4 and we will come to the right hand side of 4. And so to come to the right hand side of 4, that is to come to 10, where do we have the address of 10 stored? We have address of 10 stored in 4 right, because 10 is right child of 4, correct? So that is the reason root data which is less than the number, after that when this condition becomes true, we again call the search function using root right, because since root data is lesser than the number, we would be ignoring totally the left hand side of the root and we will coming to the right hand side. So we are coming to the right hand side of the root and we are again calling the search function with the right hand side of the root and the number. So at this point what happens? at this point, this search function is again getting called with the value 10 and the number 13, because 10 is 4 right. So again the search algorithm starts. Root is not null, 10 is not null, so it is true. We will enter root data less than number. So let's check. 10 is lesser than 13, 10 is lesser than 13, that is true. So since 10 is lesser than 13, again we have to ignore the left hand side and we have to move to the right hand side. So that is what we are doing. Since this if condition has become true, we will again call the search algorithm with root right and the number. So we will again call the search algorithm with root right. Now what is root right? That is 15. 10 right is 15. So the search algorithm will be again called with 15 and 13. 15 is the root and 13 is the number to be searched. So again the algorithm will start. Root not is equals to null is true. We enter the if condition. Root data lesser than the number. Now currently the root data is 15, correct? So 15 lesser than the number is false. So since this is false, we will come to the else if condition. Now what else if condition is asking us? Whether the root data is greater than the number. So 15 is greater than the number. So now since 15 is greater than the number, that means we have to ignore the right hand side and we have to search the number only towards the left of 15. Why? Because of the nature of binary search tree. Any number lesser than the root will always lie on the left. So since root data is greater than the number, that means number is lesser, so it has to lie on the left hand side. So that is why search is getting called with root left and the number. So we are calling the search with root left. What is the value of root? 15. So we are calling the search with root left, that is 15 left. So that is the node 13 and the number 13. So when the search starts, again root not is equals to null, that is true. We will enter the if condition. Root data lesser than the number will be false because root data is 13. Root data greater than the number will also be false. So since the number is not greater or it is lesser than the number, so that means it is equal, or in other words we have actually found the number in the tree. So since this condition and this condition both are false, so in the else part we are returning a 1 to show that the search has been a success. Right? So that is how a successful search works. Now let us see whether how this function will work if we try to search out a number, say 1. We want to search out the number 1, right? So if we want to search out the number 1, let's say, then again we have to call this function using the root of the tree and the number that we are trying to search. So we will be calling search root. What is the root value or root node? 4. So we will calling the search function using 4, 1. 4 is the root of the tree and 1 is the number that we are trying to find out. If root not is equals to null, so obviously 4 is not null. We will enter the if condition. If root data lesser than the number. Now what is the value of the root data? 4. Is it lesser than the number? No. So since root data is not lesser than the number, it will come to the if else if part. Sorry, it will come to the else if part. Root data greater than the number. 4 greater than the number? Yes. So since 4 is greater than the number, 4 is greater than 1. So 1 can only lie on the left hand side. So again the search is getting called with root left. So again from here we are calling search with root left. Now what is root left? 4 left is 2. So we are calling the number with 2, comma 1. That is the number that we are searching. So again the function starts. Root not is equals to null is true. Root data less than the number is false. Root data greater than the number is true. So again the search is getting called with root left. Now let us see what is happening. We are at this 2. Now 2 is greater than 1. So we are calling the search function with root left. Now what is root left? What is 2 left? Null. So that is why now we are calling the search function with null and the number 1. Right? So as the search is getting called, root not equals to null, this becomes false. Now you have to understand this. While searching, we have come across a place where we have come across a node which does not have a left child, but the node has to lie on the left hand side of that particular node. If one ever exists, one would exist on the left hand side of 2 in this binary search tree, because that is the nature. We have reached a point where 2 does not have a left child. So that means this number 1 cannot exist in this binary search tree. Again, I am telling you. If 1 exists in this tree, 1 has to exist as the left child of 2. But left child of 2 is null. That means we have reached a point where 1 does not exist in this tree. So that is the reason if root not is equals to null, when this condition becomes false, we straight away come to the else part and we return a 0, indicating that the number has not been found. So in a binary search tree, either you will get the number or you will reach a point where the node value becomes null to indicate that the number does not exist in the tree. So that is how binary search tree search function works in a recursive manner.